thank you for everybody coming along. Introduction to functional safety for fluid power. Got to say, not always the most interesting topic, so we'll try and keep it a little light-hearted. It's a fairly small group, so do feel free to sort of interact a little bit and ask some questions. The reason we're here, the reason I'm here, I work for Fortress. Fortress Safety is all about providing the best safety solutions and saving lives. And when we look at the number of accidents, the number of injuries that does happen in industry still at the moment, despite all of the leaps and all of the advances that we've seen across there, there's still lots of good things we can do. I still feel that we can make a difference to make that happen, and nowhere more so than in that fluid power industry at the moment. So for me, the aim today is to get a little bit of understanding of why that's important, what we want to do, and then get a real high-level introduction of what we're thinking about when it's functional safety and what that means in fluid power. So I'm Technical Director at Fortress, so I've been involved with the engineering team for 10 years or so now, and then my colleague Matt.
Hello, yes, so not quite as long maybe. So I run around, the joke I suppose is I quite like standards. So I'm part of our safety services team, so training and other pieces to do with understanding why these very useful documents that people have spent quite a lot of time on developing can be helpful to understand and use to meet whether that's requirements, but also to understand how to address a lot of the problems we have when it comes to machinery. To run through a little bit of what we're going to cover today, functional safety is a pretty hefty topic. So in the next 30 minutes, we're only going to sort of touch the water, the top of the water, I suppose. We really are going to just introduce some broad basic concepts. Very happy to have more conversations later. We're going to try our best not to throw too many technical terms and pieces. If anything, we've taken them out because there is a lot of detail we can go into when it comes to functional safety. But this morning's session is really to, I guess, understand where this concept comes from and how we need to think about it when it comes to fluid power.
Yeah, indeed. And absolutely, Matt does love standards. I can absolutely attest to that. But today, it isn't a job of trying to show how much we know about the standard numbers and throwing them out there, nor is it, if you've seen some of the other functional safety stuff, where you get deeply into the modelling reliability and lots of formulas and calculations. It's nothing about that. It's really understanding why is it important, what is that top level bit. If you want to go and dig into those details, there's lots of really good courses. We can help point you in the right direction, but it's just, can you go out of this room today with a better understanding of what functional safety means? And for me, it's nothing more than this. You know, functional safety is used as a risk reduction measure. It's a thing to keep people safe and stop injuries happening. And would you be happy to put your hands in there because there's a safety system in there? Do you believe that that really is going to keep you safe? Is that system, is that thing, is it as good as going and turning that ball valve? Is it that same level of safety that you would expect from full isolation that you can achieve with a control system? And we want to run through how that is and some of those places where maybe that goes wrong at the moment and the ways to put that right for today. I think if we look at these pictures here, this is probably the sort of stuff we see on the news coming out as that picture of the modern factory. We see lots of robotic arms, we see lots of conveyors, we see lots of automation. Also, if we look closely on here, you'll see lots of safety and risk reduction measures on there. We can probably look across here and see a light curtain stopping us getting into that sort of area. We can see some e-stops, we can even see some interlocks and things on those gates. They're all about making sure that when somebody accesses that area, we've looked at what hazards are inside there and we made sure that they're safe when we go in there. And what we want to understand is a little bit of how big is that risk when we go in there, what is likely to happen, and make sure that we have a system that is reliable, that that level of reliability matches up to that level of risk. So this robot, to me, looks as if it might be mounted and come up and down here. That can only just reach that light curtain, and maybe what you could get from it was a slight bruise or a bash on the hand. Then maybe that level of reliability is different to if this is on a slide, it's going to come up here, and it could be a full crushing, it could be a life-changing or even a fatality on there. And I think you can already start to see that when you look at that, you might want different levels of reliability on there, and it wouldn't matter whether that's an electrical control system, whether it's a conveyor, a motor, it's a robot arm, or whether that's something hydraulic that's driven in there. You know, when we look at these systems, hydraulics still one of the highest power densities that we see anywhere in industry, still particularly dangerous. How are we going to keep people safe? In just the way we saw that automated factory, when we see people running about the Amazon warehouses and running in between robots, how are we going to achieve that same level when it comes to here? Do we always have to go back to that lockout, tagout, to that full isolation? Or can we still take some of that efficiency, some of that control system, some of all of those advances we've seen since PLCs, since safety controllers come in, and can we apply that to the hydraulic, pneumatic, to that fluid-powered industry in just the same way as we do everywhere else in industry?
And I think that's the thing, if you compare the last couple of slides, right, I think we've got quite used to what modern industry looks like, right? E-stops, interlocks, other devices for that sensing. But I think being conscious of how fluid power fits into that, I guess, those words of functional safety is the thing that's often missed.
Absolutely.
So, I did joke that I quite like standards. There are loads of standards out there. I'm not going to read through all of these. It's really important to understand the intention of standards and where they come from, what they mean in different places. The content within those have been very carefully constructed to help us spot the things that other people have spotted in the past as well, whether that's giving us a guidance through a process of how to do an effective risk assessment, but also more specific requirements when it comes to functional safety. I'm not going to read out any of the numbers. We'll mention a couple of numbers maybe later on. I'll cheat a little bit. But it's really about understanding that if you know or appreciate what content is within those standards, it can move you towards being able to have those effective solutions, especially knowing that that ultimate goal, right, is to keep people safe, to be compliant when it comes to that regulation. And depending on how that standard is written or what that document is, it will help you directly meet those regulatory needs or put you a good chunk of the way towards thinking about all the things you might have missed. When we look at standards for risk assessment, it makes us think about hazards or certain situations. When we have type C or specific standards for certain machines where it says you really should be doing this, or these are additional hazards or tasks that might be specific to your machine. I know it's challenging sometimes, especially if you haven't been exposed to standards in the past. It's hard not to see them sometimes as a list of requirements that not necessarily always lots of fun to deal with. Standards are really helpful for us to be able to do the right thing, reduce that risk after identifying those tasks and those hazards, and do so in a reliable way too.
I did tell you Matt loves standards, and I come from the opposite point of view, that probably just as Matt talked about there, when I started as a junior engineer, I always saw them as a barrier or a thing I had to meet, and it was always, I'd never quite spotted that piece. As I moved through the career and I've worked in different places, and particularly with Fortress, I now see what a valuable resource they are, and when we're not sure how to do something or we want a best practice, a great way to go back there. But I do feel that that fluid power area is particularly lacking at the moment, where I can go and get guidance on lots of different machines. I can get guidance at that type B, that middle level of just best industry practice for electrical and electronic and even software systems. It's really difficult to find. We can look at the bottom two there that actually talk specifically about hydraulic and pneumatics, and I can find one line on about page 6 that says, oh, if you're going to use a control system, maybe have a look at 13849 if you want to, the other stuff, but then it all gets a bit scary and they jump back into hydraulics or pneumatics and that safe world. So now, as some of the work I do with BSI and the HSE with Paul Grady, who runs that committee there's actually a new standard that will come out probably in the next year, 18 months, that will actually take that little one line and say, well, maybe look at this, and actually give some guidance to what that's about. And I've got to admit, Paul Grady is quite a tenacious character at the HSE, so when he gets an idea, he does tend to try and push that, so I think it will get mentioned a lot more as we go through.
So before we jump into talking about functional safety in a bit more detail, what it is, what are those core principles and why, it's worth calling out the fact that we don't jump down this rabbit hole and focus on a solution right at the beginning. I know everybody likes to say, well, what's in your risk assessment? But that really is because that's what allows us to understand what regulation are we trying to meet, what standards do we have at our disposal to help us guide through that process and make some of those decisions. And based on the information we have, there'll be situations where we have to go through full isolation of those energy sources, and that's the most appropriate way to handle those tasks, right? If I'm taking my machines apart or I'm commissioning right at those early stages, of course I don't want those power sources connected. Again, we've only got 30 minutes, we're not jumping into that whole decision matrix and process, but it's a really key bit to take out, is that first stop is always, what are we doing? What is that risk assessment? Before jumping down any of those avenues. So on the left, we've got the idea of that lockout, tagout, energy isolation. On the right, on that slide, right, was the idea of using other ways or alternative methods, depending on where you are in the world, of reducing the risks you've identified through that risk assessment. I'd say a couple of standards numbers. BS 14100 is a really handy standard. It's a standard about the control of hazardous energy. Again, we're going to jump into functional safety in a moment, but think about those different situations where we may be more likely to use full isolation of those energy sources, and other situations during the normal intervention, the normal operation, more frequent interventions, where it may be more appropriate to rely on those reliable control systems with functional safety. So I'm not going to read out all of the information in that table. We're definitely not going through the decision process of what is or isn't a good idea. But be conscious that useful information within that British standard, but those variety of different situations. Sometimes we need to lock out, right? That's the most appropriate way to prevent people from being exposed to risk. In other situations, it may be appropriate to use those light curtains, to use those interlocks. What we'll see over the next 20 or so minutes is we have to think all the way across that control system, not just the things that are sensing, detecting, or opening, but how are we controlling those sources of energy in a reliable way.
So we've mentioned it a few times. Matt's talked about that idea of when would we use functional safety or when would we use full isolation, and that idea of that efficiency, if it's a part of the normal operating procedure, if it's running, we want to be able to get in there, do a task and get out. But I often find that a lot of the courses around this will go into the detail, they'll do all the calculations, but everybody sort of comes out going, well, I know all the calculations, I know the standard numbers, but I don't really know what it is, what does that mean? And all it means is we're going to use that control system. Pretty much every machine I go to now has a control system of some sort, looking after what it does, what operations go through there. And we're going to use that control system across the entire piece. So we'll have some inputs detecting whether a gate's open and shut, whether somebody's gone through a light curtain, whether a presence detection device has picked somebody up in an area that they should be. It'll use that logic in the control system to decide what needs to happen to keep them safe. And then there'll be some sort of actuator on the other end that allows that to stop and put it into the safe state. And that might be a VFD motor controller, that might be a robot controller with a safety input to it that puts it into the safe state, maybe a contactor, or maybe it's a valve. And we need to have, no matter what that energy source is, we've got to have high reliability, because right back to that picture at the start, would you be happy putting your hand into that press? I don't want some of these bits to be really reliable. If I'm going to put my hand between the jaws of that press, I want all of those bits to be reliable. I don't want to know that this thing is ProfiSafe and it's the latest, greatest, and it's going to do it and only have a failure once every 50,000 years. If I'm going to get a bit of debris in the media on the hydraulic valve and it's going to stick in the wrong position and still bring that down and chop my hand off. So really simple concept that seems to be quite poorly explained across there is we're going to use the control system, we're going to have some sensors, and we're going to actuate something, and we're going to make it safe in a really reliable way. And absolutely, when we look at these sort of things, we want to split it into those three areas. We already talked about those sensors. we've got this logic part, we've got that output of whatever it may be, and you may find that we talk about the control system. If we look at some of the bits, we talk about the safety related parts. So you'll often find there's a separate piece. This won't just be using the sensor that is the usual end stop on something. This will have a separate piece, an interlocker guard, a safety light curtain. We might have a PLC that looks like it's all in one, but if it's Siemens, it'll have the little yellow flashes. Actually, within that box, there's two separate parts. There's the general control, and then there's a separate safety one. That's running a separate program, that's running separate checks. Maybe even it's a completely separate device, and it's a safety relay, as you can see out on our stand in the hall, that actually is running that. And even if the control system goes mad, tries to do something awful when it's in there, we've got a separate way of controlling these outputs and making sure we've isolated that energy, that there's nothing going to happen even if the control system tries to do something while somebody's in that hazardous area. And I think this is the point we made earlier, talking about that robot. Where is it? What is it doing? We talk lots about risk assessments, and all that is saying is what might happen and what's the consequence of that? How likely is it to happen? Is there a chance of somebody getting out of the way? And if it's a bad thing that's likely to happen more often, we've got to make that system reliable enough for people to trust that that's going to keep them safe. Otherwise, we're not going to be able to take any of those efficiency gains. We're just always going to go off and isolate it, or we're going to end up in an even worse situation where somebody does trust something that isn't reliable enough to keep them safe. So I think now what we can do is go on and look at a little bit of how those concepts of having that input, logic and output go together, and what things we can do to make a system reliable, and how does that apply when it comes to putting valves or to hydraulic power systems in there.
And so on the slide that Rob showed a moment ago, right, we've split everything out from that input, that logic, to that output. And the conversation that often happens when it comes to functional safety or the use of these control systems is that the folks that had to learn some of these topics first were those electrical engineers, were those control engineers that were looking at those inputs, finding these new fancy safety relays a little while ago now, right? And thinking about the design of these systems. We had a nice little discussion before the session, right, about that interaction between different specialities, right? Do our mechanical, do our fluid power experts have that same level of awareness of the requirements, the expectations of those electrical systems? If we've done all of that work to make sure we've got reliable inputs and a hefty and reliable logic controller, but we failed at the last hurdle because we've not thought about how that system is going to control those fluid power sources, for example. So a pretty simple slide. How reliable is it? Again, you can go on multi-day courses to understand the ins and outs, lots of detail behind what starts off as a pretty simple diagram. But whenever we're trying to, well, hopefully design anything, but especially design something that is going to reduce risk, keep people safe, we're going to be applying some broad principles. Have we, I guess, applied good engineering design? Have we thought about some of those failure modes? Now, failure modes might be considered in terms of their impact on productivity, but we're talking about safety now, right? What are those situations where I'm not able to execute what we call that safety function? If I open that door, how do I know that my press is actually going to have stopped moving? Now, there's lots of ways to do that and do that correctly, right? It's not just me looking over to Rob and going, I reckon that looks good enough, and we all say yes and sign up on it. Calculations work in the background to build as part of that evidence to say, we've made these choices for these reasons, and this is why it all adds up and makes sense. But when we look at these simple diagrams, right, if we had just one input device talking to one logic device, talking to one output, we need to think about what those possible faults can be, and also whether we can detect them. Even if we have really reliable individual components, there's lots of other things that could cause issues, cause faults, cause some pretty upsetting situations. I sometimes make the comment that it doesn't matter how reliable your components are, if you connect them together with some pieces of wet string, you can quickly foresee that there are things that could go wrong there. And it's about taking that awareness when we look at some of those systems. So if a really basic system could be an input and a logic and output, how does something with a higher level of reliability account for some of the faults that we might see? So things have got a little bit more complicated. And again, this is still a simplification of some of the topics that we need to understand to really know how to apply functional safety. But straight away, we've doubled up on a couple of things. What does this allow us to do? By having two channels to communicate information, we're more confident that we're going to essentially send that message, right? How do I know whether that contactor has turned off? Well, if I'm sending that information to two contactors, at least one of them should get that message. I'm going to have that redundancy to make sure that I execute, again, what we call that safety function. I've got an input, I'm processing that information, I want something to happen to those outputs. So, thinking about dual channel, and maybe that's a term that some people have or haven't heard before, is, I guess, one of the, fundamental levels of understanding why redundancy may be needed. And again, in an electrical context, we've been pretty comfortable with this for quite a while. When it comes to those outputs, though, what does that mean when it comes to fluid power? Can I reliably control those energy sources as part of that full function? The other bit is that we've gone through sometimes considerable work, expense, review, technical time and investment to get that redundancy. We need to be able to detect if something has gone wrong. Having that redundancy but no way of monitoring or discovering whether something needs to be addressed isn't particularly helpful. And we'll see that in a little bit. So loads of detail behind these principles. Again, lots of numbers, lots of very interesting standards, I promise. But those core principles of if we have redundancy, that moves us in the right direction, but we also need to think about what monitoring is required. And combined in the right way, we're going to be more confident that when we operate that device, trip that light curtain, those pneumatic, those hydraulic sources of power should be controlled as well. So let's look at a little example again, deliberately keeping things fairly simple, just with some jazzy photos. So think about our inputs, right? Whether that's a light curtain, a contact sensor, right? Remember, all through this, we're thinking about those engineering principles. Devices built for those purposes, making sure you're using the right thing. Again, suitable to be used in these safety functions and systems. Rob's already mentioned, right, whether that's a Siemens safety PLC or other approaches, right, we need those logic devices. Those logic components do a really important job. They're checking our inputs. Have we got a fault in those devices? Have only one of them worked, or maybe only one of those contacts has functioned as expected? If we detect the loss of that redundancy, we've done our job, because we can go and fix it before we lose that final line when it comes to being able to do what we want to. So this example has called out, we put a nice little yellow box over that output. And we'll go through this in a bit more detail in a moment. But what we want to be considering is, as part of our redundancy, as part of our monitoring, when a component doesn't act as it should do, are we going to detect it? Are we going to make sure that's going to be addressed before we can do anything else? And if we do those things in the right way, hopefully, we'll be reliably and consistently not exposing people to some of those risks and hazards because of the way we've designed our system. It's annoying not being able to reset and start up your machine. It's better to be in that situation, though, rather than continuing not realizing that something much worse has happened in the background.
And I don't know how true it rings with you guys, but I spend a lot of my time now going out to customer sites, to talking to people, helping them understand how to make machines safe and what parts they may need to bring together to do that. And when we look through, we see lots of bits where this bit has that dual redundancy. And in fact, even if we go to that electrical piece, it will have that dual contactor, and it'll have little auxiliary contacts on the back. And that will feed that arrow back this way to say, yes, if one failed and one doesn't. But when we get to that hydraulic control, we still have all of this bit doubled up here, but we just have one of these. We don't have this bit. And that's not to say that that valve's not reliable. That's not to say that that's not a good part. And that if we go back to that single level, if we had it all single here, in some circumstances, that might be fine. If we're going to get a slight bruise, we know that happens. It's going to be picked up on maintenance before we're exposed to it. That's fine, we can have single channel. If we're in those really dangerous places where we're looking for that high reliability to match it with that risk, why is it acceptable to have one valve here when everything else in that system has two? Why is it acceptable to have that one valve there with only the arrow going that way, turning it off, not some monitoring coming back that way that's really reliable to tell us what position that spool's in, what position that's holding, is that in the right stuff? Because just as Matt was talking about there, about that redundancy, if we have that redundancy without monitoring, all we're doing is putting off that inevitable a little bit longer. This part fails, but we've got two of them. That's fine. We can still carry out that safety function. We still stop the machine. But without that monitoring coming back, unless we know about that, we think everything's working fine because that second one stepped in and done the job, made it stop. If we then find that the debris that's in the media that's caused this valve to stop shuttling properly actually works its way round, and also there's some dirt in the media that gets to this one's going to stop as well. And quite often we find those incidents happen relatively close together. If we don't have that monitoring, all you've done is made a marginally more reliable. You've just put off the inevitable for a little bit longer. So we need to make sure that not only do we have redundancy, but we have it all the way through the system, right up to those valves, to those actuators at the back piece, and you have monitoring feeding back in, whether it's from the inputs, comparing, yes, both switches went at once, or whether it's on the outputs, yes, both contactors went, one hadn't welded, or both spools have shuttled within that valve. And we can see that exactly with the sort of devices we have here available at the moment. So here, pretty simple stuff, and I will, feeling a little bit at the wrong end of this because Fortress knows lots about functional safety. I suspect there's a lot more people here today that know a lot more about hydraulics and pneumatics than us, but at a very simplified level, we've got here directional control valve operating something in and out exactly as it would be. All we've done now is added that safety valve at the front, effectively like we have that control relays operating what should be, and a main contactor at the front end we put here. It's invisible to the system as it runs. When we're operating normally, this goes through, directional control valve decides where the ram sits, and then bleeds it back through tank. All working fine, no problems at all. What we now have is that safety system has operated. Maybe something's gone wrong in the control, so we're still trying to drive this cylinder. But what we've got here is that input, that control. So we've opened a gate, the logic has picked it up, and now we've driven that safety valve on a completely separate hardware system into the safe state. So here we're blocking that pressure coming in, and everything else is bleeding back to the tank. So we've taken away that hazardous energy that might be compressing. We've taken away the chance of a hose burst and spraying things onto fire. We've taken away the chance of a leak and a fluid injection piece because we've drained away all of that hazardous energy, just like you would be turning the ball valve there. And of course, we've got this monitored with the switches on the back end, so that's going back into the control system to know that's happened. If we have that same situation now, but we go back to that dirty media, something's got in there, there's some debris that's stopping that valve spool, that spool moving in the valve. Well, now we've still got this first one passing through, but we do have that redundancy. So if we trace it through, pressure's passed through, but we're still blocked at the second valve. Pressure already in the system or anything accumulated up here is still coming its way back through. It's bleeding to tank here, it's passing straight through and still back to tank. So we've still achieved that same level of safety. But what we also do is know we have these switches, we have that monitoring feeding back that goes back into the control system to say, I'm not going to allow you to reset. I'm not going to allow you to put this back into the running state because I know something is wrong until you go and service that and show me that I can operate both of those and use that redundant channel next time. That system's not going to allow you to go back there. suddenly I'm feeling a little bit happier about putting my hand into the jaws of that press under this system than I was back when I thought any bit of dirt in the media is going to stop this and allow that to happen as it goes through. And that's exactly what we do. This isn't a big complicated piece. We've talked about lots of standards. We've said there could be lots of calculations on the back of here, but this is not a difficult thing to implement. All we've done is effectively put an invisible piece of hardware back and fed it into the control system. There's a really nice segregation. If we go back to this one, we talked a little bit earlier, and Matt mentioned it, that segregation between maybe the hydraulics falls under the mechanical team, but that safety system falls under the electrical team. If you draw a little line down here, electrical team, very used to working with redundant switches on their contactors on all the other pieces. A little bit of pipe work on this side, seems pretty standard stuff for the hydraulic engineers on that side. We can separate that piece, still have it in there. In terms of the system, it operates pretty simply. So whether it's a new install, or even if we're going back and looking at pure regulations, if we look in the equipment that some of these pipe mills that I've been to have been running for a fair while, certainly a little bit longer than I've been running, that's for certain. And I don't think this was considered when they were put in there, but it's pretty easy to go in to add that into the system, to get back where that's safe. When we have that HSE inspection, when we have that audit, we've got the ability to go and meet those and show that we're meeting their simple systems. An upgrade exactly on a pipe mill as we saw in the previous versions. We've got all our control stacks over here running exactly as they were. They put a new valve stand in the front end of it and then just carried out that isolation, put it back into the control system, the same as they'd already got running for the conveyors, for the lateral movements of the pipes up and down on the system. And suddenly we've gone from no safety, or no functional safety, no ability to have reliable and confidence in the fact that that system's going to be safe when somebody enters the area, to getting that right up to PLE, to that top level of safety where we'd say, well, actually there's a risk of crushing, there's a severe or fatal injury risk there that people are exposed to regularly as they go into maintain. We've got a system that's reliable enough to do that. We don't have to go and fully isolate. We don't have to go and turn the pump off every time.
We almost got all the way through without saying the word PL.
And
we try that as we go through, right? Like some of you may have heard terms like categories of architecture and performance levels, right? And mean time to dangerous failure. All of those things are stuff in the background to make sure we're doing those things properly. And as you said, right, you'll have different folks in different parts of your organisations who are more familiar or comfortable with those terms. Hopefully what we've gone through this morning, though, in a little over 30 minutes, has been to help emphasise how useful that awareness can be, right? Whether it's your electrical folks, your mechanical folks, your fluid power folks, realising that there might be a little bit more work to do here, or something that has been spotted, or as Rob said, right, maybe when a system was made quite a while ago, a couple of things just weren't considered. It's those early bits of awareness and catching and then later conversations that allow people to go back, maybe look at some standards, and see what other approaches may be helpful. We've not thrown lots of standard numbers, and again, there's loads of others if you do want more. We like to throw out some webinars from time to time. If you've, well, I'll give you a break from my voice for a little bit first. Again, lots of information out in the world more generally. We make some information and share that as well. I guess thanks very much for coming along, and very happy to talk through any questions that anybody has.
Why do you think the fluid power industry then has been lacking behind more so than the electrical industry? And bearing in mind the size of the machinery, the forces that you mentioned.
I think it is just the way that's developed. So there was a company, competitor, partner, depending on how you see, Pilz, I think did an excellent job late 90s, early noughties, around going and educating that electrical market to say, you need that separate system, you need that safety relay. And I think before that, with systems throughout, there was an understanding of perhaps there was this reliability thing, but we didn't really know how to do it. But because of that starting point in the electrical world, that was their market they went out and talked to. They didn't deal, they didn't have products available for there. And that actually, as what was probably just a really, really clever marketing campaign back in the day, has actually driven the direction of that safety falls for the electrical engineer, and then hydraulics still sits under the mechanical teams. And I think it's just that awareness, and all I've hoped that we can do today is take it right back from lots of people do get injured. You're absolutely right, big power density, big machines. It's really not that difficult to make that change across, but I think there's just a lack of awareness when we go and talk to the FPA as the industry group, even when we come into the NFPC here and talk to some of the lecturers and things. It's not something that's been drilled in there in first principles like other bits. And I think there's a little bit of, oh no, that's somebody else's world, and they hear about PLs and SILs and calculations. And a lot of the time it isn't necessary. That's a great way for checking it and a great way for proving that system. What you're really doing is draining that energy off just the same way you would isolate with a ball valve, and just doing that with the control system. So I think there's still a lot of education and awareness to do that, but I think that is all it is. Once people know what it is, once we get that message out there, I think it's really easy to bring those two disciplines back up to the same level and just make everyone in industry a little safer.
Where does legal rights come in as an owner with this equipment, or you're installing it? What legal rights have you got to be careful of? Is there a lot of legal rights that you've got to avail?
Yeah, so I mean this is health and safety at work, so as whoever's operating that machine, certainly in the UK, has that fundamental requirement to do there. It is part of CE marking, so if you buy machines in, the manufacturer, the supplier of that machine has rights to do it, but there is just again that lack of awareness that very few people are checking. So I think you will find even with CE mark machines, you may find that you will have that little diagram with the 6 boxes on.
Yeah.
You'll find those left-hand 4, the inputs and the logic are just as they should be. But on the right-hand side there, maybe when it comes to some of that fluid power, it isn't. And that should be the manufacturer's responsibility, but ultimately the safety of workers in the UK always lies with the employer to make sure that's happened and that's in the right place. And even more so when pure regulations, does that mean?
Yeah.
Yeah. So even if we go back to the pipe mill, even at the point that was installed, that was perfectly acceptable and met that legislative requirements.
Yeah.
You've now got a requirement, a regulation there, UK stature, to say you need to go and assess that, and does it still meet an appropriate level for the risks that are out there.
I suppose most companies don't repure a machine, do they, unless there's been a substantial change, or, if the machine's sat there and it's been the same old stuff for the last 50 years, they probably think, oh, we're not considering anything with it in terms of legislation, or...
I think that's what they thought, but I think if you read it, it's a requirement to maintain that and make sure it's
there. If you did repure
there.
it might be pulled up on it, and you've not got this redundancy.
And it's not actually as scary as it seems once you put that risk assessment that Matt talked in place, when you go, yeah, these are the things we looked at, maybe we find some gaps, but it's not usually that difficult to do. We sell things now where it's one that often gets missed and pulled up on a pure assessment is that unexpected startup. So the safety system stops it, but what stops you being in there, buried under the conveyor or in the jaws, and somebody else comes along and goes, nobody in there, restarts it. So there's purely mechanical pieces that sit alongside it and just add it in, and suddenly you've got a risk assessment now, you've got a documented process to say, I've thought about this, I've put something in place, and now we're back to a good point, that residual risk is fine. So I think as soon as people understand it and just take those little steps, it's not as scary as sitting there thinking, what have I got in my factory that's going to kill someone? There's ways to get round that, it just needs to take those first few steps to make it happen.
Yeah.
So going back then, like as you've been shown for the hydraulic, the dual channel contactor equivalent to the dual channel direction control valve then, is that something now that machine manufacturers have got to put in, or is that something that you're still trying to implement within the safety integrity level of the machine?
So the manufacturer needs to run their risk assessment and they need to decide. So there is no, you won't find any regulation or even any standard that says you must fit a one of those.
Yes.
What it will say is you've got to assess what the risk is. So if a person can enter there, if they can get themselves in the jaws of that machine, they've got to say, okay, and that happens reasonably regularly. They've got to find a way to stop that. Now, that could be go and fully isolate, but if that's going to happen regularly, then there's probably an operational requirement that says I don't want to go and fully isolate my whole machine or my whole line just to go in and remove that piece or that broken.
Yeah, you've got people that naturally become lazy or find an easy way of doing things, so they're not going to isolate every time they go and make it.
So when you look even at the machinery directive or the regulations, it will be, it's in normal use and foreseeable misuse. So that's, you know, an operator, we're looking at the moment about a hydraulic ram on the back of a RCV, a refuse collection vehicle. Somebody went into the area, which they shouldn't have done because there was a bit of debris, there was some rubbish on the back of that bin lorry. They've knocked it in. The lorry has thought they were a bin. It's come up, tipped them off the feet and compacted them in the back of there. And that's not normal use. People could see, oh, well, they shouldn't have been standing there, but very much it's foreseeable misuse. And again, that's being picked up at the moment.
Yeah, I think the problem is that most hydraulic equipment, it just comes under the general standards. There are no specific standards for each item of equipment. The only one I'm aware of is the presses, hydraulic presses. They have a specific standard, and it tells you, in more detail about the safety systems.
Yeah, absolutely. And that
hydraulic, any other hydraulic machinery, it's all
and even
risk
at that
assessments, and then you've got to work it out for yourself.
and even at that generic type B, so the standards split into types. So there's type A, which is really general at the top. Type B is like that 4414, the bits, and and type C is the specific to a press.
I'm old enough to remember the company called Bosch before they got bought out, or they bought Rexroth, I'm not quite sure where it was. And they did a lot of work on presses, and they had specific ranges of safety valves designed for presses.
Yeah.
And they sort of got absorbed into the Rexroth range, and it's all slowly disappeared.
And gets there. And I think you're absolutely right. There's not a lot of information. There's like a balers and things. There's some bits in there. But even when you then go up to that type B and say, well, there's not a specific requirement for my machine, I'll use that generic industry piece. That's exactly where I go back to that. There's one line on page 6 that says you might have a think about it.
4413 from an hydraulic point of view is just a waste of space, to be honest. I mean, I come across it now and again because it gets specified for all the jobs I tend to work on, and you can see a fault on the system, but you go back to the standard to try and find out to sort it out, and it just nothing there.
And that's exactly
you
where
can do this, or if you want to, you can do that, or if you don't want to, just don't do anything.
Don't worry about it. And that's exactly where that new guidance piece is. So if you do have any interest in standards development, or even just want to input into the committee through there, that would be really useful. And the same goes for anybody in industry. If you see that gap, there are teams of people sat there trying to make this better and trying to give that information back out and available to people. So there's active work at the moment going on with that.
Yeah.
And there are some places where we have a bit more information that we're used to. There's a handy US standard which has quite a few examples, and they deliberately include quite a lot of fluid power examples just to be able to, I guess, set that scene a little bit when you're discussing functional safety. Of course, you're considering fluid power as well. As you said, right, if you think about where we are when it comes to presses, right, we've got regulations, we've got really clear Type C standards, expectations for inspections, etc. If you compare where that is to some of the other things that we should be doing, a lot of those things probably, but we don't yet have that clear definition of standards in a Type C context. But actually, following those Type A, following those Type B, you may end up with a lot of those approaches. Again, it's about having the right skills and assessments in the right place.
You know, Fortress, the whole bit of Fortress, and the reason I like working there is that saving lives by providing the best safety solutions. Of course, we make some money out of providing that equipment and doing it, but can help you design a hydraulic system, but if you have customers or you have people with questions around that functional safety about how do we go about it, we're very happy to come out and support. Matt sits teaching courses on a lot of these B11. Steve goes around visiting customers, making that happen. Myself and Jenny sit as the team looking at some of those on developing the standards and things. We're very happy to share that knowledge to try and save more lives and make that better. So do feel free to reach out and ask some questions if there is anything we can support with.
Just looking at your basic design of the two redundancy valves on the
Yeah.
direction control, would you give a customer any information on why you would not use a typical spool which could cause soot, because that one of those redundancy valves don't come in for, I don't know, 6 or 7 months time, or would you direct them to a poppet type valve or a valve that doesn't soot up?
Yeah, there can be. There's so when we look at the methods for monitoring things, there's some really good ways to do that. And again, if ask Matt about some standards,
Yeah.
it tells you some good things to do. So if you come and look at any of our interlocks, it talks about a direct drive action
Yeah, yeah.
and the fact that you've got switches and you can know if that moves into the wrong position, and irrelevant of whether it's a pinion moved by a tongue on a gate or
Yeah.
whether it's a spool, you know that switch is going to smash and break open and go to the safe
Yeah.
state.
Yeah.
So although there is that greater risk on the silting or not being able to move, we're actually able to do some really good stuff on that direct drive action and the
Look
monitoring
into that side.
and the direct
Yeah.
bit.
Yeah.
And you know,
Because
a
that
little
could be a
bit-
safety issue in itself, couldn't it?
indeed,
You know,
there's that
yeah.
piece, and that's
Yeah.
why that monitoring as well as redundancy is super important.
Yeah.
And it's the same with any safety piece with or component within a system. You could go and make your own interlocks, you could go and make your own light curtains, but that bit of understanding, that going through, that doing the testing to what it is. So some of the samples we've got on there, we noticed is that this one's done the 1.3 million cycles to go through and prove what it is, and then the FMEA assessment at the end. So by buying it as a block, that information gets provided to run all the nasty calculations that we haven't talked about today, and to consider some of those choices of is it the right one or not.
Because it's that information that informs, again, whether as a user or the designer of the machine, what are really the important bits, right? There's a difference between I need to turn it off, I need to turn it off within this certain amount of time, right?
Yeah.
Saying I've turned it off but it took 6 times as long as normal doesn't help us in a lot of situations, right? So there's loads of things that will come up as part of that
Yeah.
assessment by the manufacturer of
Yeah.
the machine, or later by user of equipment who's taken a closer look and maybe realise some other things need to be looked at.
Very good.
Thank you.
I've got a question.
Oh, yeah.
How does time and use come into play? So, for instance, if you had a machine like a press, but it was for a test application where you're only using it for 1 day, rather than using it for the next 10 years straight, how much safety do you need to put in? So, for instance, like light curtains, if it's like we're doing 1 test today, that's it for this machine. Obviously, it'd be impractical to put light curtains all the way around it, dual redundancy on your valves and all that sort of thing.
So again, comes back to that risk assessment, and part of that risk assessment is the severity of injury, which I think is pretty obvious, isn't it, around the, I'm going to get a bit of a nick on my finger compared to I'm going to be chopped in half. But there are also other factors around the probability of it happening and the probability to avoid. So when you do that risk assessment, if it's once a month we go in and do this test around here, well, that probability is very different to 10 times a shift I have to go and remove that or do a typical online maintenance procedure. So you immediately get a different piece there, and the mitigation factors can be different. Probably if you're doing that once a month, that's probably a really well-trained engineering team, and you can say, well, actually I'm mitigating some of these risks by training, by understanding, by making sure I've got a really well documented procedure around understanding what I'm doing for this one development process, which you probably couldn't rely on if you're saying this could be any one of 100 operators that's coming in and doing this job day in, day out. So absolutely it's right to consider, and if something, when you look at functional safety, doesn't make sense, if you're sitting there looking there thinking, I've got to do all this stuff for my whatever day. No, that's a development process.
I've heard the
You've got to
acronym BACWAG, like best available technology without excess to cost. But I don't know if that's actually true, if that holds in court.
Yeah, indeed, you'll see there's a slide that we took out and moved down, and it's, you know, you never get to zero risk. There's always a residual risk and what's considered acceptable, and some of that may be done by functional safety, some of that may be done by other procedural means like training, like supervision. Your best bit, you know, let's hope nobody ends up in court, but the best way to keep out of there and be in a good place if you don't is just having that documented to say, we've applied that here, it's different to what we would do in production, but there's all these ancillary things that are going on with that.